So we discussed about the particle dynamics. We read about particle dynamics, and we also read about rigid body dynamics. And now we are into the last topic, that is fluid dynamics. We are into fluid dynamics. Okay, so we have studied these three topics. Rigid body dynamics. We have to study fluid dynamics. So first of all, I'll discuss with you about the approach of studying fluid dynamics. How do you approach the system? See, fluid dynamics is a system of infinitely many particles. It's a system of infinitely many particles. In fact, you will also say that even rigid body dynamics is also a system of infinitely many particles. You can also say this. Rigid body is also a system of infinitely many particles. But there is a difference in this system of infinitely many particles and this system of infinitely many particles. I'll also tell you one more system which is also a system of infinitely many particles, that is gas system. Gaseous system is also a system of infinitely many particles. This is also a system of infinitely many particles. But there is huge difference in this system, and this system. Actually, though all of them are system of infinitely many particles, but there is a basic difference in the system, and due to which we have difference in the approach. We have difference in the approach of studying these systems. Alright. So in this rigid body dynamics, though it is system of infinitely many particles, but all these particles are not independent of each other. The motion of these infinitely many particles are not independent of each other. Motion is not independent of each other. Motion of one particle is related to the other particle. Motion of one particle is related to the other particles. The particles are strongly coupled to each other. The particles are strongly coupled to each other through different covalent bonds. Right? They are not free to move independently with respect to each other. The motion of one particle correlates to the motion of other particle. Like if I have, say, this kind of, say, a body, this is a solid, then this point cannot move with respect to this point. The motion of this point, say P, is not independent of motion of this point Q. Motion of point P is not independent of the motion of point Q. P and Q are correlated. P and Q are correlated. They are not independent. They are correlated to each other. So these particles are not independent of each other. Get your point or not? So because they are solids. Rigid body are what? They are solids. They are strongly coupled to each other. The intermolecular forces, the cohesive forces among the particles is very strong. The cohesive forces among the particles are very strong. So when cohesive forces among the particles are very strong, the motion of these particles are not independent of each other. There is enough to study the motion of one particle and just correlate the motion of other particle to the motion of this particle. This is enough to just study the motion of one particle. We can call this center of mass particle. And then the motion of other particle is related to the motion of this particle by the expression. We write it as V equals to VCM plus omega cross R. The motion can be of two kinds, translation or rotation plus translation. So if the body is undergoing a general motion, rotation plus translation is just enough to study the motion of center of mass. That gives us a good idea that, if I study the motion of center of mass, when you have a solid which is moving, it's undergoing a general motion, and general motion involves what? Translation plus rotation. So it's just enough to study the motion of center of mass and the rotation over the axis passing to center of mass, and you can just tell me the velocity of any other particle on the solids by this relation, V is equal to VCM plus omega cross R. So this system, though this system infinitely many particles, but there is strong cohesive force among the particles, so it's just enough to study the motion of center of mass and motion about center of mass. It's just enough to read a motion of center of mass and motion about center of mass. Suppose we have a classroom. Suppose in school days we used to go for a picnic, right? And if our class consists of say 50 students, we have 50 students, and we go for some outing, say we go for a picnic, right? We go for a picnic, P-I-C-N-I-C, okay, we go for the picnic. So if all these 50 students are very good friend of each other, we are very good friend of each other, when we are very good friend of each other, if somebody want to study our motion, he don't have to study the motion of each student. He can just study motion of one of us and correlate the motion of other student with respect to that student, right? In fact, what I'm saying is, if I have a strong cohesive group of 50 students and somebody want to study our motion, where we are going, since we are strongly related to each other, we are very good friends, there is a strong cohesive force among each other. So it's the motion of the studying that motion is quite easy. If there is a strong group of 50 people, they are always together, they are very strong friends, they are very good friends, there is strong cohesive force among those people, then it's easy to study the motion of that group, because you have to just study the motion of one person and the motion of other people can be just related to that person. I can just pick one person who is maybe the topper of the classroom, most beloved of all. So I can just study the motion of topper and topper of the classroom, and then I can correlate the motion of other student with respect to the motion of that topper student, and I can just correlate. So here in all these particles, the point which is very important is center of mass. So once I study the center of mass and motion about center of mass, I can get the motion of every particles. It's always easier to read a very strong cohesive group. If you have 10 people, there is strong cohesion. Like if we have a family, it's a very strong cohesive group. Like if we have a family of 5 people, right? If we have a family of 2 parents and three childs, right? I am a family of 5 people, right? So if you have a family of 5 people, family is what? Family is institution. Family is a strong group. So motion of one person is correlated to the motion of the other person, right? Motion of one person is correlated to the other person. So it's just enough to study the motion of one person and you are able to study the whole system. So that's the rigid body. Rigid body is the study of solids. Study of solids, where the 2 particles, the distributed 2 particles, remain same with respect to time. Getting a point? On the other extreme lies a gaseous system. On the other extreme lies a gaseous system, where motion of the particles are independent of each other. Motion of ith particle has nothing to do with the motion of jth particle. Motion of ith particle has nothing to do with the motion of jth particle. That's the gaseous system. And the approach of studying this system is quite different. Approach of studying this is quite different. We go for statistical approach, right? We go for statistical approach, or we go for thermodynamic approach. We go for statistical approach or we go for thermodynamic approach. That's quite different approach. In thermodynamic approach, we do not run after every particle. We just define some macroscopic variables with the system, associated with the system, and we try to study how those macroscopic variables like P, V, T, pressure, volume, temperature, entropy, how these are changing with time. Because these macroscopic variables ultimately depends on the motion of gaseous molecules. So change in this macroscopic variable gives us good idea about how the particles are moving. In a statistical approach, we do not associate the macroscopic variable. We go for the physical quantity which is possessed by the particles themselves, like energy, linear momentum, velocity, speeds. They are the physical quantity which is possessed not by the system, it is possessed by the molecules themselves, the gaseous molecules themselves. And we try to see what fraction of gaseous molecules are falling in the range, say V to V plus dV, or Vx to Vx plus dVx, like this. So the approach is quite different. That's based on the fact that the motion of one molecule is independent of the motion of the other molecule. Whereas in case of fluid, this is in between the two extremes. This is one extreme, this is the other extreme. This lies in between the solids and gases. I can't say that there is strong cohesive group like solids. It's not so less cohesive that I can treat it as gas. The motion of one particle is related to the motion of the particle, but the relation is not as strong as solids, and the relation is not as weak as gaseous system. So the motion of particles, motion of particles are related to each other. Motion of particles are related to each other. So that's called fluid system. That's the fluid system. Like say water. The water molecules, the molecules are not independent of each other. Neither they are forming so strong cohesive group that I can treat it as rigid body. So the approach is different from what we do in rigid body dynamics. The approach is different from what we do in gaseous system. So what should be the approach? What should be the approach of studying fluid dynamics? I'm just saying the current I've discussed with you rigid body dynamics and gaseous system, and now I want to give some contrast how we approach the fluid dynamics. How we go for the fluid dynamics? I told you fluid dynamics, we are into a system of infinitely many particles where the cohesive forces among the particles are not so strong that I can follow the approach what we follow in rigid body dynamics, and the cohesive force is not so weak that I treat them in the gaseous system. This is not extreme. This is transition between solid and gaseous system. Right? Fluid system is a transition between solids and the gaseous system. So the approach is quite different over here. What can be the approach? See, whenever you come across such a system, see, we have two approaches. We can have two approaches. One is called I can say Lagrangian approach, and other is Eulerian approach. Lagrangian approach and Eulerian approach. In Lagrangian approach, whenever you have a system of many particles, one way to study the system is to run after every particle, to see how each particle is moving, how the physical quantity associated with each particle is changing. So Lagrangian approach involves running after every particle, right? Like if you have seen cricket match, how many people are in there in cricket match? 11 players on one side and 2 players of the other team, 2 batsmen and 11 fielders, right? So we have 13 particles. We have 13 people playing a match. 13 people playing the match, say 11 plus 2. So here we follow Lagrangian approach. We run after every player. If you want to see the motion of all these people, we run after every people. We just try to understand the motion of every person, right? Here, if you want to track the motion of system, if you want to study the mechanism of system, you have to You track the motion of every particle. You track the motion of two batsmen. You track the motion of fielders, bowlers, everyone. Right? In case of even football match, you track the motion of every person. You track the motion of every person. Right? So you are following Lagrangian approach. You are following Lagrangian approach. You are tracking the motion of every person. So what is Eulerian approach now? And I'll tell you which approach is applicable to fluids. You will understand yourself only. What do you do in Eulerian approach? Have you ever went for marathon? How many people participate in the marathon? Say 10,000, right? We have in Delhi marathon, half marathon, more than even 10,000. And how much distance you have to cover? 40 kilometers. Or if it is half marathon, it's 20 kilometers. Now, if I have to track the motion of 10,000 people, what should be our approach? Will the Lagrangian approach will be good? Is it better to have a Lagrangian approach? Should we track the motion of every player? Oh, today you have CCTV, you can do that. But even marathon was held 20 years back also. So how to track the motion of these 10,000 people? They have to cover a distance of 40 kilometers. And usually the marathon is held on the road. You can't have a playground of 40 kilometers. So usually we are holding a marathon on the road, right? And there can be shortcuts. There can be shortcuts. So we have to avoid those shortcuts. We have to see that no participant takes a short route, or no participant in between rides on bicycle or bike or scooter. We have to prevent all those things, right? So how will you do that? If you are a manager, if you are asked to manage the marathon, will you have say 1,000 referees, like in cricket match, to track the motion of 13 people? How many referees you have? I think you have 2 referees on the ground and 1 referee in the pavilion, I think, no? Stadium, who is watching through some CCTVs. So we have 3 referees in fact. So for 13 people you have 3 referees. So ratio comes to be say 5:1, say maximum 4:1, more than 4:1. So for 2 person you have for 5 person you have 1 referee. So if we go that way, then I need, if I have to follow Lagrangian approach, I may require 2,000 referees. So 2,000 referees is a huge number. So it means you have 10,000 participants and 2,000 referees running with them. It looks ridiculous. 2,000 referees. Do you know usually for what purpose marathon is held? Marathon is held for charitable purpose. Like the money which is collected from the participant, they are charged some fees, say 10 rupees, 50 rupees. Then the money which is collected goes for charitable purpose. And if we have to pay this 2,000 referees, then I think the money which will be collected won't be enough to even pay the referees even. So this is not a good approach. We are holding marathon for charitable purpose, and the money which has been collected, the expenditure is more than the revenue. It's not a good idea. So how to manage it then? This is not a good idea. It's not a good idea. So how will you manage? What we can do is, instead of running after every participant, we can, suppose this is a route, we can have some checkpoints. We can have some checkpoints. Checkpoint 1, we can have some checkpoint over here, we can have some checkpoint over here. And these checkpoints are strategic positions. They are such a position that if somebody takes a shortcut, he or she will be missing the checkpoints. I'll just have some checkpoints which are located at the strategic positions such that if anybody takes a shortcut in between, he'll be missing one of the checkpoints. And I can just have 4 or 5 referees over here. They'll be just sitting, they won't be running. They'll be sitting over here with a desk and a chair, right? I'll make them sit over here. And what they have to do? They just have to track the motion of any person who passes from here. They have to track the motion of any person who passes from here. I can just, when the marathon starts from here, say, marathon starts from here, it's a starting point, I can give one token. I can give, see if there are 3 checkpoints, I'll give 3 tokens to each player. And I'll give them instruction that you have to submit token number 1 over here, token number 2 over here, token number 3 over here. Right? You have to submit 1 token at each checkpoint. Getting a point? So, if somebody takes a shortcut, he will be missing one of the checkpoint and his token won't be available at the checkpoint. Right? And he will be disqualified. So, instead of running after every player, every participant, we just sit at strategic locations and try to track the motion of every particle which is crossing that point. We try to track the motion of every particle which is crossing that point. We are not running after each participant. We just sit at one point, few points, and track the motion of any particle which is crossing that point. Right? That's called Eulerian approach. And that is the approach that we follow in fluid dynamics. In the whole fluid dynamics, we don't run after fluid particles. We don't run after fluid particles. Neither we are interested. We are not interested in one of the fluid particle. We are interested at points. We choose some strategic positions. Like say this is a beaker, this is a vessel, right? And this is an orifice, the water is coming out. I am not interested in all these fluid particles. I am interested in the fluid particle over here, say A, at what rate it's going down, and I am interested in fluid particle which is coming out. So I am interested in this point, point B. I am interested in point A over here, and I am interested in point B. I am interested in point A, and I am interested in point B. I am interested in what is the velocity with which the level is going down and what is the velocity with the fluid is coming out. So these are my strategic positions. I will be sitting over here and tracking the motion of every fluid particle passing through these points. So that's called Eulerian approach, and we follow this approach. We follow this Eulerian approach over here. We are following the Eulerian approach over here. Right? This is how we go for this fluid dynamics. We don't run after every particle. Right? We just sit at few positions, few strategic positions, try to track the motion of each fluid particle passing through that point. Okay, I think it's okay, right? Thank you very much.